In this video, we're going to be talking about rates of change of a function, and mostly average rates of change. But first, net change in a function. So the net change in the function f on the interval a to b is given by f of b minus f of a. Really, what I'm trying to remind you is that we get a difference in a function by taking two function values and subtracting them. So the height of a tree at time t is given by the function h, where h is measured in meters, t is measured in years. What's the net change in h? Okay, so what we're saying is that the net change would be h of 10 minus h of 2. So that's the height of the tree at 10 years, which is 15, minus h of 2, the height of the tree at 2 years, which was 1.5, and that's going to be 13.5. And what that means is that the tree grew 13.5 meters from t equals 2 years to t equals 10 years. And then it says, oh, okay, over the time intervals 3 to 5 and 7 to 10, so like here and there, the tree grew by 4 meters. And it asks, during which time interval was the tree growing faster? And I asked that question in my classes, and most people were confidently saying that happened faster over the time interval 3 to 5 because it took less time for it to grow 4 meters. And, intuitively we know that means that it grew faster. But what we were really doing there was we were taking those 4 meters of growth and we were dividing them by the length of time it took. And since we divided by a lower number, we got a higher rate of change. What we were really doing, we were taking an average rate of change. And what we're saying mathematically here is that, if we divide the increase of 4 meters by 2 years, we're seeing an increased 2 meters per year. And if we divided that increase of 4 by 3, we would have a lower number, 1.333 meters per year. But that meters per year, that kind of points us towards what we're doing here. This is the rate of growth that we're saying when we take a net change and we divide by, some sort of time interval or input interval. So our definition of average rate of change is going to be same as it was in Algebra 1 and hopefully Algebra 2. It's rise over run, f of b minus f of a over b minus a. Same as y2 minus y1 over x2 minus x1. Okay, and so now we're going to analyze the average rate of change of the height of the tree for each of the time intervals indicated by the data in the table, and we'll determine which part of its life the tree was growing the fastest. All right, so maybe I'll start from the right, because I think in class we always started from the left. So on the time interval 7 to 10, I already did this one. Okay, but same idea. Really emphasize it. From t equals 7 to t equals 10. The average rate of change, average rate of change of h on the time interval 7 to 10 is going to equal h of 10. Now I could do h of 7 minus h of 10 if I wanted. I would just need to make sure to divide by 7 minus 10. In general, I'm going to start with a greater number. H of 10 minus h of 7 divided by 10 minus 7. F of b minus f of a divided by b minus a. Then I can look up those values from the table. 15 minus 11 divided by 10 minus 7. And that was equal to 4 over 3. And so maybe I'll just put that in, and I'm going to make a new row for this table just for average rate of change. So get rid of that. I'll say AROC, short for average rate of change. So on the interval 7 to 10, we determined that average rate of change was 4/3. All right. Now, for the other ones, I'm going to go a little bit faster. I'm going to say, all right, if I increase from 6 to 11, that's an increase of 5, while x, or t in this case, the input value increased by 2. Okay, from t equals 3 to t equals 5, h increased by 4. Okay, we already did that. 4 divided by 2. And then from 1.5 to 2, that was an increase of 0.5 divided by 3 minus 2 is 1. All right. And now we can see, all right, we've got all of our average rates of change computed, and if it's asking when it was growing the fastest, that would be when it had the greatest average rate of change. And although we saw that 4 over 2 was bigger than 4 over 3, 4 over 2 is not bigger than 5 over 2, so that's going to be the greatest rate of change. So I'd say tree is growing the fastest during the time interval 5 to 7. So 5 less than or equal to t less than or equal to 7 based on the average rate of change being the greatest, 5 divided by 2. I kind of already talked about this a little bit before we even got into really defining average rate of change, but the units for rate of change for the function f are going to be the units of f divided by the units of x. Okay, but then, in the case that it wasn't f of x, if we were just talking about inputs and outputs, I would say that the units for the rate of change are going to be units of output divided by units of input. So to go back to the height of the tree example, these average rates of change that we were computing, these were telling us, the growth rate, and it was telling us the number of meters per year. But that's what I was just telling you. The units of the average rate of change are the units of the output divided by the units of input. In this case, the units of h divided by the units of t. So this is going to be all measured in meters divided by years, or meters per year. All right, next situation. We've got a file that's downloading to a computer, and the amount that has downloaded already is modeled by the function f of t, where t is the time in seconds since the start of the download, and f is measured in megabits. At t equals 1 second, 200 megabits had downloaded, and at t equals 5 seconds, 1,400 megabits had downloaded. And it's going to ask us, what's the average rate of change of f on the time interval 1 to 5? All right, so we're going to bring in our formula. And this is a formula that we are just called to know in AP Precalc. That the average rate of change of a function is given by f of b minus f of a over b minus a, or rise over run, or however you're going to remember it. But we need to be able to just know that formula. So what we're looking for here is f of 5 minus f of 1 divided by 5 minus 1. And so they told us, f is the amount of file that has downloaded. They told us two values. Okay, at time t equals 5, 1,400 megabits had downloaded, so that's 1,400 is f of 5, minus f of 1 is 200. They said at 1 second, 200 had downloaded, divided by 5 minus 1 is 4. Okay, so 1,400 minus 200 is 1,200 divided by 4. We do need to simplify in this class. That's going to equal 300. Right now, and if they ask about the units of the rate of change, okay, we need to go back and we need to look at the units of f and the units of t. Okay, so they're going to tell us that in the statement of the question, for sure. So f is measured in megabits. That would be helpful. And t is measured in seconds. All right, so we're going to go over here and we're going to say, all right, the units are going to be units of f divided by units of t, which were megabits per second. And you can say megabits divided by seconds, you can say megabits per second. In words, you can express yourself however you want. Okay, but that's going to be the units of the average rate of change of f with respect to t. All right, and now we're going to bring in just a new scenario and kind of take it a little bit farther. So snow is accumulating outside of a balcony door during a storm. At time t hours, there are a of t inches of snow outside the door. Okay, so find the average rate of change for a on the time interval 2 to 12. Okay, bring in the formula. Grab the values from the table to fill in the formula for this context. And get ourselves a number. We got 0.29. But then it says using appropriate units, interpret its meaning in the context of the snowstorm. Okay, so I'm going to start with the units, right? Because that's what I just told you how to do. So the units for the rate of change of A will be inches per hour. And I think that oftentimes the units can kind of lead you to the direction of the meaning. Inches per hour, okay, that would be like the rate at which the height of the snow outside the door was increasing or decreasing. And so we'll say that, at between time t equals 2 hours and t equals 12 hours, on average, the height of the snow was going up 0.29 inches each hour. Okay, and so I would say, maybe in the words, maybe something like rate of snow accumulation. At this point, there's no wrong answer, right? And so if I did the same thing and found the average rate of change of A for the time interval 20 to 24 hours, I would find that it's going to be negative because A decreased. And units of this rate will still be the same because it's still the rate of change of the same function. So it's negative 1/2 inches per hour. Okay, so if A is the height of the snowstorm, or not the snowstorm, but the amount of snow that's sitting outside the door, and it has a negative rate, it means that the actual height is going to be going down. Okay, so I might say this is related to like the rate of snow melt or something like that. So what I'm trying to get at here is that, if we look at the average rates of change of something and we see that they're positive or if they're negative, what that's really telling us is if the function is increasing or decreasing. And that's going to be related to the definition of where a function is increasing and decreasing that we'll take in the next lesson. Okay, so what I'm going to say here for now, we're going to say increasing, that'll be where our average rate of change is positive, and decreasing, that'll just be where our average rate of change is negative. Now, for this question down at the bottom, is the amount of snow at the door increasing or decreasing at time t equals 20? I'm just going to say there's not enough information for us to say, right? It's going from 3 to 4 back to 2. But we don't know if 4 was the actual maximum amount of snow in inches that was sitting outside the door, or if the maximum was actually a little bit bigger than 4, and it was, by the time it was 4 at t equals 20, it was on the way down, or maybe it was still accumulating and the maximum was bigger than 4 at a time later than 20. We just don't have enough information to say. If we wanted to know, it would be helpful for us to have information about A at values of t much closer to 20, like maybe 19 and 21. But that discussion is really getting more into the calculus of this scenario, and it's a pre-cal class, so we're just going to stick to computing average rates of change for now. Alright, now we're going to speed up a little bit. So here's the graph of a function f. Find the average rate of change over the given intervals and interpret the results. I'm going to do the first one for you, and then I want you to do the rest of these on your own. Okay, so on the interval 0 to 2, I get negative 1/2. And I'm going to write the same interpretation every time because I really am trying to train you on this interpretation. I'm going to say that on average is so key because it's the average rate of change. F is decreasing 1/2 for every increase of x of 1. But I think that the clearer way to say that, it decreases 1/2 per x. Okay, so each time x increases by 1, we expect y to decrease by 1/2, is what we're saying there. Okay, so you try the same on 3 to 6, 3 to 7, 6 to 7, and 0 to 7, and write out that same explanation for each of them. Okay, we're going to say that, if the rate of change is negative, the function is decreasing this many y's per x. You could say decreases 1/2 y for every x. Or something like that. You can write it in your own words. But you should do this with a video pause because I'm just going to bring in the answers here in just a couple seconds. Alright, there they are. Okay, so that was a lot of fries overrun, at least it was for me. And so, but, I think that was good for us. I wrote it a couple of different ways. In the second one I said on average f decreases 2/3 each time x increases by 1. That's true. The one where the average rate of change was 0, I said on average f is not changing. Okay, we know that in reality it decreased and then increased. Okay, so it's not really giving a very accurate picture of the behavior of f over that interval, but in terms of starting and ending, it does. And then I said increased by 2 y's per x on one of these, and okay, so increase because I saw a positive average rate of change. And then the last one said on average f decreases by 3/7 per x on the interval 0 to 7. And I guess the reason I finished with that one is that just again doesn't give you a very accurate interpretation of what's going on with this function over the interval 0 to 7. On the interval 0 to 7, there's a lot of action. It kind of increases a little bit, then it decreases a lot, then it kind of recovers some, and that average rate of change of negative 3/7 only encapsulates these 2 points that I just, colored in blue. But what I should probably remind you is something that you knew about in Algebra 1 for this, rise over run thing, that this average rate of change, this represents the slope of the line that connects these 2 points. And you probably already knew that, but I thought I'd just remind you of this fact while we're looking at the graph of a function and talking about its average rates of change. Alright, here's another opportunity for you to practice your computing your average rates of change. Okay, so here's a table of values for the function f. find the average rate of change of f on the given intervals. When is f changing the most? That's kind of a loaded question, right? Changing the most. But, compute all of those and think about it yourself. What does that mean to be changing the most? So again, you're going to want to do this with the video paused because I'm just going to bring in the answers to keep this from being a super long video. Okay, so pause now, work it, and then check your answers against mine. Alright, so there you have it. A bunch of average rates of change again. Hopefully you're getting enough practice here with computing rise over run. Okay, we need you to be well practiced in this and able to execute this accurately. Okay, as far as changing the most, I'd say, undergoing the greatest amount of net change, either positive or negative, that would probably be right here, where I'm seeing an average rate of change of -6. Okay, so from x equals 2 to x equals 3, the function going down from 9 to 3, that seems to be the most change that I'm seeing. But that's the kind of vague question that we won't be asking you on a quiz or a test in AP Pre-Cal. I just thought I'd throw out there for just food for thought. All right, next I've got this interesting type of example problem that is honestly not something that I've offered in my pre-calculus class before, but we saw an item in AP Classroom that we thought was interesting, we might like to use, and so we're preparing you for it by, using this new problem type. So basically we're going to give you the average rate of change of h of x on some given intervals and ask you to fill out a table. Okay, this is really, it's getting out of multiple choice questions, so it's not like you're going to have to find all these things, but you will have to find one of these values, and you're going to have to use the average rate of change to get the total change, and then go from there. So I'm going to be really detailed on this one and show you how to fill out the whole table, and then I'm going to let you try it on your own on the one that's underneath it in the notes book. Okay, so we're going to start over here with the average rate of change of h, and then we're going to make a new row for total change. And I'm going to actually divide this up so that this is actually its own row here. All right, and what I'm proposing is that we're going to need to find the width of the interval in x, okay, and then multiply that by the average rate of change to get the total amount of change in h of x or in y or whatever our output is. So I think, I'm going to label this as, okay, in x we went up +1, 1 to 3 is +2, 3 to 6 is x increasing by 3, and 6 to 7 is an increase in 1. To use the terminology I used in the definitions, that would be delta x. Okay, and then the total change, okay, if I went from x equals 0 and x equals 1, average rate of change of -5, okay, that's decreasing 5 for every increase of 1 in x, okay, well, x will increase 1, or decreased 5 y's per x, that was part of why I was, introducing that language. I would say here, that the total change is -5. And then on the next one, if I increased 4 per x, or 4 y's per x, 4 times 2 would be +8. But in case you don't believe me, I'm going to bring in a little bit of algebra to the side here. Alright, so what I'm saying is, if the average rate of change of this function f of x on the interval 1 to 3 is 4, then that means that 4 is equal to that fraction over there, f of 3 minus f of 1 divided by 3 minus 1. So I could say, over here, equals 4. Okay, and then as a result, I could multiply both sides of that equation by 2, by that 3 minus 1, and I could say that, okay, f of 3 minus f of 1, that's going to equal 4 times 2. Or more specifically, 4 times 3 minus 1, which is going to be that +8 that I wrote down there. Okay, also, I could go all the way back to the beginning and say, okay, this is the net change, f of 3 minus f of 1, and I'm going to get the net change by taking the average rate of change and multiplying by the width of the interval on which we took the average. All right, so I'm going to say +8 there. For the other ones, +3 multiplied by 2 would be a net increase in 6, and an average rate of change of 7 over a width of an interval of 1 is just going to cause me to increase by 7. Okay, then I can go down here to the table and say, all right, as I'm going from 4 to the next one, I'm going to have to use that -5, okay, because that's telling me the total change of h on the interval x equals 0 to x equals 1. So 4 minus 5 would be -1. Okay. And then I will say, all right, the next one, to go from h of 1 to h of 3, I'm going to have to add 8. So negative 1 plus 8, that's going to be 7. And then I'm just going to keep doing the same thing. Oops. To go from x equals 3 to x equals 6, h increased by 6, so 7 plus 6 is going to be 13. And then for the last one, okay, if I'm thinking about going from h of 6 to h of 7, I'm going to increase by 7, and 13 plus 7, that's going to be equal to 20. All right, so in summary, what we did there was we took the average rate of change table, we translated that into total change for the function over those given intervals, and then we actually made those total changes happen on the real table down below. All right, so you can try this one on your own here. The table below gives the average rates of change of the function j on certain intervals. Use those intervals to find the total change in the function and fill in the missing values in the table. Okay, I am going to point out that these ones over here to the left, you're going to want to be careful with those when you're trying this on your own before you check your answer against mine. Those are a little tricky. We have to think backwards on those, and I will be honest, I got tricked on the first time I did it. So I was just passing that on to you. That's a good place to be careful. Okay, so again, I'm going to bring in my answer so you can check it. So you're going to want to just like pause now and work it on your own, and then come back when you've tried it. All right, there it is. I got a total change row by multiplying the average rate of change by the widths of the intervals they represented. And then I really definitely started with the red ones because those are easier. Went forward, but listing out the total change on the appropriate interval. But then I did the same thing backwards with the blue numbers, and I let those total changes guide me to what the number needed to be. And then having those down there, it was really nice that I could check that the arithmetic worked out, that negative 11 plus 18 is 7, and 7 minus 3 is 4. Okay, so I feel good about that when I've got the numbers written down below like that. All right, now 4 more. And this is really just a chance for us to review some of the things that we did in the last unit, right? You see those negative exponents, the fraction exponent. So this is another chance you're going to want to do this one on your own, because I'm not going to just like work this and narrate every step. You want to work with it paused so I can bring in the answers here in just a few seconds, and you can check it and see if you're doing this right. And then if you're not, you can bring that to me and I can work with you on those specific skills that were from the earlier topics. All right, there we go. So, with these ones that are defined algebraically, this is really just, practice makes perfect. We need to make sure that we're doing it consistently and we're not doing like run over rise, right? We're not doing the x's on top and y's on bottom, and that we're not getting mixed up, that we are in fact, like, for instance, over here, doing f of 3 minus f of 1 divided by 3 minus 1. It's okay if we do f of 1 minus f of 3 on top. We just need to be doing 1 minus 3 on bottom to make sure that we're sticking to f of b minus f of a divided by b minus a. Okay, now the last thing I need to show you in this video is about linear and quadratic functions and their rates of change. Okay, so the rate of change of a linear function is constant for any interval. Okay, so notice up here the average rate of change that I got here for this linear function was 5, which also happened to be the slope of that line. Okay, that's not a coincidence, and that's what we're saying. This will happen for any interval. Okay, so, and I'm going to say that not only is the rate of change of the linear function a constant, it's the constant that's given by the slope of the line. So I'm going to go just real quickly through this, and if you're not interested in this, feel free to fast forward 20 seconds or whatever. I'm going to plug in b and a into h of x, and I'll get h of b is 5b minus 3, and h of a is 5a minus 3. I'm going to subtract them. And then I'll also, just factor, because it'll help me in a second. But then I'll divide by b minus a to find the average rate of change of h of x on the interval a to b. And I'll see that, if I do a little bit of canceling here, strategic canceling, I've got, b minus a over b minus a, that's just 1. This is going to be equal to 5. So I've shown that the average rate of change of h will be constant on any interval a to b, and that constant is going to be 5. All right, and so just to be real specific here we've got a couple of linear functions, okay? And I know these are linear functions because they're mx plus b, they're a degree 1 polynomial. We haven't talked too much about the degree of polynomial yet, but I assume you heard about that a little bit in Algebra 2. And we're going to look at these tables of values. Okay, but what I'm saying in yellow is that these are linear functions. Okay, if we were to consider like the average rate of change of these functions, we could say, y2 minus y1, or f of b minus f of a over b minus a. Over here, from -2 to +1, that's an increase of 3. Okay, and then x, well, it just increased by 1 each time. Okay, and then same story here. Each time, we're increasing by 3. And the x values in the table are all spaced out by 1, so the average rate of change will always be this +3. And then the same thing will happen over on the right. We're over here we see 11 to 7, that's a decrease of 4. But if we divide by the width of the x interval, we'll get -4/2 is that same -2 that's the slope of the line. And the same thing over here, -4, width of 2, -4, width of 2, and so on, -4, width of 2. So really just showing you that you're going to get a constant average rate of change. The average rate of change is going to be the same on every interval. With quadratic, you may have heard this before. In Texas, this is one of the standards that we have to hit in Algebra 1 and in Algebra 2. So if you're pre-cal and you're from Texas, you've heard this at least twice. But for a quadratic function, you might have heard that the second differences are constant. The way we're going to say this in AP pre-cal is that the average rates of change over consecutive equal length input value intervals, they form a linear pattern. Okay, so I'll show you what I mean here. Okay, we're going to make a table of values for this quadratic function w of x equals x squared. Okay, and I've filled that out for you because I know you know how to square these numbers. If I make an average rate of change column here, and I go from 16 to 4, that's a decrease of 12. And I divide by the 2, and that would be average rate of change is -6. And then from 4 to 0, that's a decrease of 4. So a decrease of 4 when x got increased by 2, that would be an average rate of change of -2. Okay, from 0 to 4, that's an increase in 4 divided by the width of the interval is 2, that's +2. And then 4 to 16 is +12 divided by 2 is +6. Okay, now I've got these average rates of change. And I think it's important for me to point out I've got evenly spaced x's in my table. The terminology we're using is consecutive equal length input value intervals, equally spaced x's. Okay, average rates of change form a linear pattern. Okay, and what we mean there is by form a linear pattern is that if we look at the average rates of change of those things, it's going to be constant. That's what we said linear meant, was that it had a constant rate of change. The average rate of change was constant over any interval. So on this interval, the rates of change form a linear pattern. So that increased by 4, -2 to +2, that's an increase in 4, and then from 2 to 6 is also an increase in 4. So that's that constant second difference thing that you may have seen in the past. So there's a couple different directions we can go with that knowledge. There's a couple different types of questions we can ask you, but for the most part, it's going to be like, okay, here's a table. Does this represent a quadratic function? You analyze the average rates of change and see if those average rates of change themselves form a linear pattern. Or we could give you part of a table and be like, hey, this represents quadratic function. Have you fill out the rest? Or we could ask certain questions about the average rates of change. But I think you'll see all of those on the homework. And I think this is where I'm going to stop. I'm close to half an hour, and it's significantly longer than I like for these videos to be. But we're just getting started off on our discussion of rates of change. We're going to have quite a bit more to say on it. But I think we bit off quite a bit of it today. And so thanks for watching. Hope it helped.